And a periodic table would be a good thing to have out as well. Okay, so here's our first question for you. The chemical properties of an element are largely a product of which of these? Would it be their protons, the number of neutrons, the number of outer electrons, which would be those valence electrons, or the number of inner electrons? So which of those give it its chemical properties? Okay, a couple more to click in. So what's actually doing the reacting in a chemical reaction? It is C, the outer electrons. Fair portion of you got that. So on that side, that blank area, write down the number of valence electrons or outer electrons. The electrons are what do the reacting. Protons stay where they are. Neutrons stay where they are. Inner electrons tend to stay where they are. Okay, we're going to look at the alkali metals first, then we're going to flip to the halogens, then we're going to look at period 3. This is a good unit for flashcards. A lot of memorization in this unit. Not so much calculations and trying example problems so much as memorization. So the alkali metals, those are group 1, which we've seen multiple times now throughout the year. And here's our next question. So will they lose or gain their one valence electron, forming a, what would their cation or anion be, and what charge would they form? So A, B, C, or D, which one would fit in? Let's see. Okay, a couple more seconds, get those last couple of answers in. Okay, and this one, and they are going to, excellent, much better percentage there. They're going to lose one to form a cation. Whenever they lose, that becomes a cation because they're more positive now than they are negative. Cation is a positively charged anion, and that would be 1 plus. So A is correct. So lose 1, cation 1 plus. Okay. Okay. So, I want you to think about when they react with nonmetals, would they form either an A, metallic bond, B, an ionic bond, or C, a covalent bond? Again, we're dealing right now with the alkali metals reacting with a nonmetal. What type of bond would they form? Metallic, ionic, or covalent? Okay. Hopefully we got a lot of B's here. Excellent. Ionic. Ionic. A metal and a nonmetal is an ionic bond. Questions so far? So, let's think about this ionic bond a little bit. So we're thinking about the ions that they form. Sodium reacts with oxygen. Which of these would form? So we're thinking ions. We need to think about the ions that they form. So we need to look at the periodic table. Sodium's an alkali metal. Oxygen is a nonmetal in column 16. going to end this one anyways. So, sodium is an alkali metal, so it has a 1+ charge. Oxygen in that second to last column is going to gain 2 electrons, so it's a 2 negative charge. When I crisscross those, I do indeed get C, Na2O. So Na was a 1+, O is a 2 negative. Crisscross those, Na2O. I need 2 Nas with a 1+ charge for every 1 oxygen with a 2 negative to cancel out and be 0 neutral overall. Okay. So alkali metals are going to have a low density. They're going to be soft and have a low melting point. And that's because each atom is only going to donate 1 electron to metallic bonding. So they're very weakly held together. We're going to do a demo tomorrow because we won't have time today with sodium in water. And the sodium is going to be soft enough for me to cut with just a regular kitchen butter knife. Normally we don't think of metals as being that soft, or I can actually cut it with a knife, just a regular old knife. As we go down the group, they get softer and softer, and they're going to have a lower melting point the further down I go. And that's because of their larger radius, which you would have seen in the 3-2 notes yesterday if you watched those last night. And that's because there's a weaker attraction between the nucleus and the valence electrons. Can anyone remember or look back at the notes you wrote down what the special, it's electron blank. What's the word that we use? Electron blank, causing the weaker attraction as we go down the group. Yeah, exactly. So we have electron shielding. There's electrons that are in the inner layers that are shielding the amount of attractive force that the electrons in the outer layers are going to feel from those protons that are in the inner layers. So they're not held as tightly. Okay, these, as we go down, are going to become more and more reactive. They're all quite reactive. They're so reactive that they're going to tarnish in air, which is why we'll see tomorrow the sodium is in oil. It's kept in oil. So these chunks of sodium that are really soft that I'm going to cut with a knife, they're kept in oil. We're going to see it start to tarnish once I take the little piece out, and we're going to see the color change on it. And that bottle that's in the oil is kept in another container that has an absorbent material around it to try to keep it even drier and away from the air as much as possible. And that's all because it so easily loses its 1 valence electron. Bless you. Okay. As we go down the group, the size increases, so that atomic radius is increasing, which means the ionization energy is going to decrease. So the amount of energy to remove an electron decreases, which means the reactivity, how reactive it is, increases as we go down. They're going to react with water quite well, which is what we'll see tomorrow with sodium. I have no ability to show you any of the lower down on the periodic table alkali metals. Sodium's the most that they'll sell to schools. It's reactive enough. Yeah, exactly. Yep, regular high schools, we can get sodium and that's it. And this reaction, it just forms sodium hydroxide, NaOH. So you can write that down as the product. When sodium and water react, we're going to form sodium hydroxide. What chemical that we've seen very recently in a lab can we use to show that we have a base? See a beautiful color change. The phenolphthalein, exactly. The little droppers of phenolphthalein that we had, we're going to oxide, or at least that it forms a base when I do this reaction tomorrow. Okay, halogens. So we're skipping over to the other end of the periodic table, not the noble gases because they're very unreactive, so they're kind of boring for us to think about. But the halogens are quite reactive. They're group 7 or 17, depending on how you number your groups. Some of the time they'll number the groups without doing the transition metals, and that's where we would get 7 for that. So here's another clicker question for you. How many valence electrons do they have? Will they gain or lose electrons, and how many? Would they form an anion or a cation? And what would their charge be? Okay, end this one, and hopefully we got a bunch of A's. Excellent. So, the halogens have 7 valence electrons and will gain 1 valence electron, forming an anion with a 1 negative charge. Perfect. Good percentage there, guys. Okay. So, we know that these halogens are going to form diatomics when they're not bonded with anything else. They're part of our magic 7. We also have oxygen, nitrogen, and hydrogen that behave that way as well. And that's, again, because they're so reactive. And here's a question for us. Oh, yeah.
Why does 18 not bond with itself then?
Which one?
18? That would be carbon.
It would, but we'll see that it's not quite as reactive because the radius is so much bigger than, say, iodine or fluorine, so it's not quite as reactive. Good question. Okay, so when halogens, which are nonmetals, react with metals, would they form an ionic or a covalent compound? And when they react with a nonmetal, would they form a covalent or an ionic compound? Okay, let's end this one. So, A is correct. When a halogen, or a nonmetal, in other words, reacts with a metal, it's ionic. And when a nonmetal and a nonmetal reacts, it's covalent. So A is the correct answer. Okay. Let's look at halogen some more. So, most ionic compounds that are formed between halogens and some metal are going to be white and soluble in water. Gets kind of boring sometimes, but most of them are. There are some insoluble halogen salts that would be good to memorize, and those are lead 2 iodide and any halide, so any of the halogens with silver. Now we're on to the next page. So, at standard temperature and pressure, we saw this thing before. STP means standard temperature and pressure. Fluorine and chlorine are both gases. Bromine is a liquid, and iodine is a solid. And that's because as we go down the group, there's stronger van der Waals forces between them. We're going to talk more about what van der Waals is later, but those are just weak forces holding them together. And those weak forces get stronger as we go down. And as we go down the group, it's less reactive. And that's because we have those bigger atoms, and so there's a weaker attraction between the nucleus and the outer electron, so it's harder for it to gain that one last electron. So there's a thought question for you next. I want you to start thinking about it. if we were to react a halogen with an alkali metal, which alkali metal and which halogen would create the most vigorous reaction? What would you suppose, Caleb? Yeah, francium and fluorine, yep. You said it the British way, very nice. Francium and fluorine probably would be the most reactive because francium is the most reactive of the alkali metals and fluorine is the most reactive of the halogens. So most likely that's probably what we would have the most vigorous reaction with. Good. Okay, so halogen displacement reactions, these are single displacement reactions. And which of these represents a single displacement reaction where we have a halogen? So we know they're going to be diatomic. Molecule. A, B, C, or D. Bless you. Let's get that last one clicked in, please. There we go. So, excellent, a lot of A's, that's good. So we have a single displacement reaction, one thing is coming in, kicking out one other thing, forming a new ionic compound. Good. What would B be? B. Decomposition. C. Synthesis. And D. Double displacement. Good. Excellent. So as we go down a group, the electronegativity increases, which means the oxidizing power decreases, and what oxidizing power is the ability to accept electrons. So if we want that first reaction to occur, the A2 plus Mb goes to B2 plus Ma, we can only have a higher halogen on the periodic table would displace or be able to displace a lower halogen. So if I had table salt, NaCl, what element would be able to come in and kick out the chlorine? Fluorine, yeah. Fluorine's the only one that would be strong enough to be able to come in and kick out the chlorine. So if it asked you, would a reaction occur between iodide, I2, and sodium chloride, what would you say? Yep, no reaction would occur. Good. Good. The iodine's not strong enough to kick out the chlorine. Okay. Period 3, we're looking across now. We're not looking at the groups up and down. We're looking at the periods across and the oxides that would form. So sodium oxide would be Na2O, magnesium oxide would be MgO, aluminum oxide would be Al2O3. And those are all metals reacting with oxygen. The oxides are all ionic, and they would conduct electricity when in the liquid phase. So if we took those crystals and heated them up enough so that they were liquid, we'd be able to put an electric charge going through it. Sodium and magnesium oxides, if we were to dissolve them in water, would form a basic solution. So if I took that sodium oxide, Na2O, and dissolved it in water, I would form sodium hydroxide, which we know is a base from the reaction that we did last week. Aluminum and silicon, though, their oxides are amphoteric, which means they could be either acidic or basic. Got a lot of good flashcards just on this slide that you could make, because I have always seen on every IB exam at least one question dealing with, would an oxide of blah 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 be basic, acidic, or amphoteric in water? It always shows up. So that would be a good one for a note card. Okay. As we keep going, We know that phosphorus, sulfur, and chlorine are all nonmetals. Their oxides are covalent because we're dealing with another nonmetal. So nonmetal is covalent. Their oxides react with water, forming strongly acidic solutions. So this is one way to make phosphoric acid. We take P4O10 plus water, forming phosphoric acid. That would probably be a good reaction to memorize as well, because I've seen that show up on tests before as well. So here's a little clue for you. If you see an H with something, you can think acid. If you see an OH with something, you can think about bases. And that's just until we get into a real discussion of what acids and bases can be defined as and what they mean. For now, though, 99% of the time when we see an OH, we know it's going to be a base. And if we see H with something, it's going to be an acid. Okay, this is just a reminder from 2 units ago, 1C. Evidence of a reaction, we see color change, formation of a precipitate, gas produced, or temperature change. Flip the page. This is also a reminder of the most common driving forces. We have formation of a solid, formation of water, transfer of electrons, formation of gas. And we're going to look specifically at that formation of a solid for the end of our notes here today. Formation of a solid, or the formation of a precipitate. Before we can talk about that, though, we need to think about what soluble and insoluble means. So if we have something that's soluble, the ions are going to dissociate in whatever solvent we're using, which most often is going to be water. And another word for this is just an electrolyte. So when we have ions that have dissociated into my solvent, we have electrolytes. So Gatorade has electrolytes because it has ions in it. So if I look at sodium and sodium chloride, it would dissolve, soluble, into sodium and chloride ions. Okay, insoluble is the opposite. The ions are going to remain bonded in solvent. They're not going to dissociate. So it is non-electrolytic. They don't form electrolytes. And an example is calcium carbonate here. Oops. Back, evildoer, back. Okay. Calcium carbonate is what's found in a lot of antacids because it reacts with acid, form carbon dioxide, helps you burp if you take that type of antacid, which can be a good thing if you have an upset stomach. And it's the main component in shelled animals, which why it makes a lot of sense why we would want something that's insoluble on shelled animals. They need that as protection, so it's good that it doesn't dissolve. Okay, so we're going to make some predictions about solubility using the solubility rules with our little wizard here. This chart will be given to you on the test. You just need to know how to use it. So, if we look, anything with a nitrate is going to be soluble. And there's no exceptions to it, so there's no unlesses. So any nitrate you ever see is going to dissolve in water. If I have something here that has an unless, that means it could potentially flip. So normally, chlorine, bromine, and iodine salts are soluble unless it contains silver, mercury, or lead. So if I had lead chloride, it's going to be insoluble. So a little refresher here. Soluble, we know, means dissolves. So if we were writing a balanced reaction, would that be SLG or AQ? AQ, yeah, so it's aqueous. Which means AQ. Okay, insoluble. Doesn't dissolve. SLGAQ. Yes, yeah. It's going to form a solid, which is a precipitate. Hmm? Yeah. I use it for precipitate. Which of these two would be a driving force for a reaction? You can look back at the top of your notes there. Yeah, the insoluble forming a precipitate. This is one of our driving forces of a reaction. Which means that if we don't form a precipitate in any of these reactions, that there's going to be no reaction occurring. So if both of our products end up being aqueous, we're going to say no reaction is likely to occur. And we'll see that in a bit here. The wizard is going to pop up some compounds, but he's going to pop them away very quickly. So we're going to watch and see what they are, and then we're going to determine if they're soluble. We'll do thumbs up, thumbs down if it's insoluble. So they're going to show up under him. KBr for our first one. KBr, soluble or insoluble? Look at the chart. KBr, would it be soluble or insoluble? Thumbs up or thumbs down? Excellent. I see a lot of thumbs up. Yeah, it is soluble because all BRs are soluble unless it's Ag, Hg, or Pb. K is none of those, so it's soluble. Good. It's going to pop up the next one under him again. BaSO4, barium sulfate, soluble or insoluble? Yeah, that falls under one of my unlesses. So it would have been soluble, but it has that Ba, so it's insoluble. Good. Okay, it's going to pop up under him again. Li2S, lithium sulfide. Soluble or insoluble? Yeah, I see a lot of thumbs down. Yeah, all sulfide compounds are going to be insoluble. Good. And then the last one, he's going to pop up here. Calcium hydroxide. Calcium hydroxide. Soluble or insoluble? I saw some wavering, but a lot of people got to the right one. So normally hydroxides are insoluble, but this one contained calcium, so it's an unless, so that means it's flipped. So it is soluble, so it would be aqueous. Good. So a precipitation reaction is the same thing as a double displacement reaction, and we're looking for a solid to be formed. So two compounds are going to exchange their cations, and the general form AB plus CD, A's and B's switch, or A's and C's switch places. Oopsies. Oh goodness gracious. Okay, and we get A bonding with D and C bonding with B. That's my general form for a precipitation or a double displacement reaction. So let's take a look. We've got silver nitrate and potassium chloride for our first ones. They're going to react, and they're both aqueous to start with, so I know I'm going to be pouring two solutions together. And I'm going to go through 4 steps to determine if a reaction has occurred, and if so, how is that reaction balanced. So let's see here. First step is to look at the ions and their charges, because we're going to have to do some crisscrossing. Step 2, the metal is going to stay where it is, and we're going to move the non-metal. Or vice versa. As long as you're consistent about the way that you're doing it, it really doesn't matter which one you flip where. The third step is to determine which, if any, is a precipitate. So which, if any, is a solid or insoluble. Because if it's not, we're not going to have a reaction. If one of them is not, we won't have a reaction. You shouldn't see it where both become a solid, unless I made a mistake somewhere. And step 4, if we did have a reaction, so if one of them is a precipitate or insoluble, which means a solid, then we get to balance it. Otherwise, we would just say no reaction, because the reaction is not going to occur. So, some images here that might help you think about what's going on. In our first reaction vessel, we've got a whole bunch of water. I didn't write down the water part there, but I've got some silver ions and some nitrate ions dissolved in it. My second reaction vessel, I have some potassium and some chlorine ions dissolved in my water. So what I'm going to do is have them switch places. The silver is going to now bond with the chlorine. So I have silver, Ag1+, and chlorine, Cl1-. They're going to crisscross. I get AgCl. Now I need to look at my chart to figure out if it's soluble or insoluble, or aqueous or solid. Yeah, insoluble. So it's a solid. We would write an S behind it, representing that it's a solid. It's the precipitate that would form. So we know that we're going to have a reaction here, but I can't balance it until I've done my other ions. So I'm going to look. I've got, putting it into solution. Okay, not dissolving. It's a solid. Now, my potassium and my nitrate are going to bond because they're my leftover stuff. So K1+, NO3 1-, they're going to crisscross. Get KNO3. And I look at my chart. Is it solid or aqueous? Aqueous, yeah. So, in my reaction vessel, I've got some potassium ions and some nitrate ions, and I've got some solid silver chloride. Now I can get to step 4, balance it. How do I get this one balanced? Yeah, I don't need to do anything. It's already balanced. I'm going to write already balanced. Yeah.
Alright, so I don't get, like, when we, like, determine, like, if it was, like, soluble or insoluble,
Okay.
how that affected the equation, how it's written.
That just depends on whether we do an S for insoluble or an AQ for soluble. That's the only thing that makes a difference in the writing out. Good question. Any